Well, if you know me, then you know that I'm not really an AI expert, but you know that I also use AI, like many people, for doing my work in climate science, especially for downscaling weather and climate forecasts for various applications in agriculture, health, water, and so on. And this nice report from Columbia University, which was commissioned by Bezos Earth Fund, and was done in collaboration with University of Albany and ESRI, which is a company that does a lot of this GIS mapping stuff. You can look it up. They looked at the landscape assessment of AI for climate and nature. Basically, they are trying to see if AI is ready for climate and nature, and what are the advances needed, what is already available, what are the issues to worry about, what are the applications that are already going on for agriculture, buildings, industries, biodiversity conservation, climate impacts, and of course climate predictions, which we have already talked about with the Google model, IBM. Everybody is doing AI-based forecasts now and so on. So that's why this report is very important, and even though I'm not an expert, we will read it together, and I have learned a bit about it to talk about it. So we will start with the basic concepts in the context of this report on landscape assessment of AI for climate and nature. Our planet is in crisis. We are experiencing biodiversity loss to such an extent that researchers suggest we are in the midst of a mass extinction event. The rampant increase in greenhouse gas emissions is leading to catastrophic climate extremes, and the hottest year ever. Records are being broken nearly annually. 2023-24 now stand at the top. Of the 9 planetary boundaries that have been identified to keep Earth livable, we have already reached 6 of them. So this planetary boundary concept is a pie chart which shows nitrogen cycle, emissions, deforestation, biodiversity loss, pollution, etc. to say there is a safe operating space, and we have crossed many of them. It's a framework, global average quantities. Not everybody agrees with it, but it's a cute thing that we should definitely learn about. Transformative system-oriented changes are urgently needed to address these challenges, yet progress toward policy ambitions to achieve these changes, such as the Paris Agreement and the Sustainable Development Goals, are off track. Well, we are not keeping up the pace needed to stay ahead of climate change impacts and so on. Artificial intelligence offers us a way to better understand these vital and complex problems, and, if applied strategically, to dramatically accelerate the pace of solutions. This report explores both the current uses of AI in climate and nature, as well as emerging opportunities as at the nexus of those fields. We are particularly focused on the development of applications that will hasten the implementation of impactful and scalable solutions while ensuring they remain trustworthy, ethical, and equitable. So AI is raising a lot of flags, especially about whether it will have its own mind and start doing crazy things out of control from us and so on, and whether everything we build and implement in terms of AI penetrating literally everyday life will be trustworthy, ethical, and equitable, right? So in that context, let's just read off the key concepts in AI, at the level that I understand it, and at the level we should all understand, because it's not about being an expert in AI, but understanding enough of the AI language so that when you use it and when it's imposed on you in various ways, you know what you are getting into, right? So artificial intelligence, AI models are computer programs that perform tasks considered sufficiently complicated to require some level of higher reasoning or intelligence. So it's linear analysis that we do, correlation, statistical analysis, etc. do not work. Then we need some non-linear higher level of reasoning or intelligence. That's why it's called artificial intelligence. Artificial neural network is a popular type of machine learning model that was inspired by the organization, structure, and function of neurons within the biological brains. It incorporates large numbers of nonlinear components arranged like neurons with connections sharing information among them. You remember the web of neurons that the brain picture always shows. And our brain is, an amazing machine. It does a lot of learning. As we are born, we are learning audiovisual cues, languages, and then we go to school, we learn to crawl, walk, run, etc., music, So artificial neural network is based along the same lines. Bioacoustic systems, they use sound information as their primary input. Similar to computer vision data, the analysis of bioacoustic data is dependent upon the task, which can include detecting, identifying, or counting items or people in images and predicting the trajectories or positions of objects. Okay, that's an application. Of course, learning is always being done when data is given, whether it's visual data, audio data, bioacoustic data, and so on. Computer vision systems derive information and meaning from visual data such as images and video. Computer vision data can be analyzed in various ways depending upon the task. This can include detecting, identifying, classifying, and segmenting images, or predicting the trajectories or positions of objects. And now it's also being used to fill the holes. So if you have old images that have lost the pixels or color and so on, AI can go in and do some magic and reconstruct the full picture in a remarkably good, impressive way. Okay, convolutional neural network. Convolutional neural network is a class of deep neural networks most commonly applied to analyzing visual images. They are used to recognize patterns and structures within images or sequences and are a cornerstone of computer vision applications. Okay. Deep learning, we already used the word, but what it means. Deep learning is a more recent type of machine learning that uses deep neural networks, i.e. with many hidden layers, to mimic the complexity and level of abstractions of human brain, and is capable of more advanced visual and language learning, deeper than artificial neural networks and so on. Digital twins make sense just in terms of, if you are aware of what you used to do before in terms of computer-aided design, computer-aided machines and so on. We used to build things on the computer, look at the 3D rendition before actually fabricating things. So digital twins are somewhat along those lines. They are sophisticated computer simulations of a process, assembly, or phenomenon aimed at mimicking a complex system with a high level of realism. They are meant to be digital counterparts or twins of real-world systems or processes that can be used to accurately, quickly, and inexpensively simulate their real-world counterparts, such as for design or evaluation of their response to specific actions. So here is a general picture. Artificial intelligence is the big umbrella under which these things fall. So you have machine learnings, where you have dozens of different machine learning methods, neural networks inside them, and deep learning with multiple hidden layers, as we said. I still have this kind of sinus problem that doesn't seem to quit. Edge AI or Tiny ML. These are AI and machine learning systems deployed in the field at low cost via power efficient devices, so little things working on their own. Using the increasing power of small computing low power systems, they do analysis that previously could only be accomplished at centralized server centers. Edge AI systems can instead make near real-time predictions or perform local actions, thus decreasing response time and promoting security and privacy of transmitting less data. You can imagine that this could be a little fly that is spying, or could be a drone that is making a decision on who to chase down and what to detect and so on and so forth. So many applications. So what is currently AI able to do? Currently, AI allows us to process and digest vast quantities of data. So AI can obviously go beyond human capacity to identify and interpret complex relationships among seemingly disparate and extremely large data sets. Automate monitoring. AI can be used to monitor environmental changes and their impact in near real time. Optimize solutions. AI can quickly sift through large volumes of data, constraints, and alternatives to find optimal or close to optimal solutions. Could be about how to observe a cyclone as it's moving along, how to predict it then with the data, and so on. Build predictive models and forecasts. So follow up. When trained on abundant data, AI can efficiently and accurately predict future outcomes, bolstering a wide range of predictions. I have already podcasts on how Google is doing that I'll post. I think I may have posted already, but we'll see soon. Develop realistic simulations of the real world. AI accelerated digital twins can allow scientists and stakeholders to experiment without risk as they explore the impact of certain actions on specific environments. Imagine making a digital twin of a particular campus like the IIT Bombay campus or a city of Mumbai, and everything is mapped, and then you're trying to see what happens when a flood comes, what actions can you take without actually taking them on the ground, but implement them in the digital twin, look at the pros and cons of it, and then go into the real world, right? And then imagine doing that for digital twin of a human body, operations, surgeries, treatments, drugs, etc. Develop realistic simulations of the real world, so that's the AI digital twins. Accelerate new discoveries. AI can lead to faster and new discoveries across a range of applications, and just in nature and environment we are finding all kinds of relations, cloud modeling, mixing in the atmosphere and the ocean, and so on and so forth. To harness AI fully, we will need to ensure data accessibility, so data sets should be made as broadly and publicly accessible as possible, so as broadly and publicly accessible as possible to engage the AI community and drive algorithmic and application developments. Again, you can think sectorally. Improve cross-disciplinary collaboration. Framing important domain questions and problems with the AI community is critical to fostering collaboration and accelerating progress. Develop clear and quantifiable benchmarks. In conjunction with the public datasets, benchmarking is critical to AI development and acceleration, so that you know what you are actually doing and these hidden layers don't become unintended consequences. Increase availability of domain-specific data. AI models are typically trained on diverse datasets, but they may lack domain-specific knowledge required for certain applications. They are physics agnostic. You give them data and they look for patterns, and without understanding the physics they can tell you what's happening, what we call data driven models. But sometimes physics is necessary, especially in biological systems. Biology is not working by any first principles like Newton's laws of motion, so it can be very complicated to figure out what is happening in the data. Maybe there is not enough data sometimes, so AI may misinterpret things as well. So data limitations we'll discuss are obviously very tricky. Moving forward with basics of AI, federated key concepts, that is federated learning. Federated learning is a specialization of machine learning applied to preserve data privacy in situations where the data in question comes from separate sources, such as medical data. It frequently uses edge AI techniques to take advantage of decentralized learning and other processing. Remember, edge is local, low energy, local decision-making learning, etc. Foundation models. A foundation model is a machine learning model that has been trained on a broad and diverse set of data to enable its application across a wide range of tasks in a self-supervised manner. For example, a model that might initially be trained on general text data from the internet, but can then be used or subsequently refined for a more specific task such as grammar and editing. So you are basically learning from other people's writing on how grammar and editing should work. This is very common now. These models learn rich representations that can then be adapted to various downstream tasks through techniques like fine-tuning on task-specific data. Let me get a sip of tea here. Generative AI. This is used a lot. Generative AI systems can generate text, images, or other data, often in response to user prompts, by learning the patterns and structure of training data and then generating new data with similar characteristics. This is in contrast with discriminative AI systems, which can only choose among alternatives or produce a single numerical value. So it's not adding value to the data. So generative AI can learn and then extrapolate it in many directions, right? Graph neural networks, graph neural networks, not neutral, graph neural networks. GNNs are a type of neural network architecture designed to operate on graph-structured data. Unlike convolutions working on 2 or 3D structures, graphs are composed of nodes or vertices and edges that connect these nodes, allowing for the representation of complex relationships and interactions between different nodes. So you can think of temperature, winds, humidity, precipitation, and those are the vertices, and then how they are related to each other and feeding back within each other, interacting with each other, and so on. Internet of Things, very broad terminology that's now used very often. We'll look at an example of Internet of Things for agriculture in this report. The Internet of Things describes devices with sensors, processing ability, software, and other technologies that connect and exchange data with other devices and systems over the Internet or other communications networks. IoT devices are frequently deployed in the field for various monitoring tasks. An agriculture example we will see, but also at home you have air conditioning, garage door, car, your phone, everything linked together, so you can remotely operate various things. Labeled data refers to data sets that have been tagged with one or more labels identifying certain properties or classifications of the data points. So the annotated data. Large language models, or LLMs, another key concept that is now mentioned very often. LLMs are foundation models that we defined here, specifically trained on language tasks. For example, these models can be trained on large amounts of text and then use that input to do question answering, summarization, translation, etc. So basically you can teach the model to speak French with the data, so you speak French to it, you speak English to it, and it translates it to French when you are communicating or traveling or trying to make some exchanges, purchases, business, whatever, right? Machine learning is a subset of AI where an algorithm learns what a system needs to know or do by training or learning on data rather than specifying the rules of the model or program. Right? So we use this terminology already, and now we are defining it later. It's a subset of AI. That's what we said in that figure that we saw here, right? So just remember these things, they are accumulating on you, so just listen as carefully as you want. And the report is available online, so you definitely can go back and read it, right? Multimodal AI uses multiple types of data inputs such as text, images, and acoustic for AI tasks. Multimodal AI is able to integrate and process data from different modalities simultaneously, allowing it to perform tasks that require a more comprehensive understanding of the world or systems than unimodal AI systems, which are limited to a single type of data. Natural language processing, another thing you hear quite often in the media, for example. NLP is a subfield of computer science and linguistics, primarily concerned with giving computers the ability to interpret, support, and manipulate human language. So it's a natural language processing. Sounds like what it is, right? Reinforcement learning. Reinforcement learning is a branch of machine learning that aims to emulate how an agent would optimally interact with an environment. This is often characterized as a sequence of multiple steps or actions that maximize the reward received over the course of or at the end of the task. So you are optimizing certain cost function or benefit you can think of. Self-supervised learning. Self-supervised learning is a machine learning paradigm that falls between supervised learning and unsupervised learning. So what is supervised learning? Supervised learning is a type of machine learning technique where the model is trained on labeled data sets. In supervised learning, the training data consists of inputs paired with the corresponding correct outputs, and the goal is to learn a function that maps the inputs to the outputs. So you have given it a pathway to go from the input and like a predictors, predictants and predictors, for example. Whereas in self-supervised learning, it's a machine learning paradigm that falls between supervised learning and unsupervised learning. So that is self-supervised learning. And unsupervised learning then is unsupervised in a type of machine learning technique where the models are trained on unlabeled data without any associated target outputs or rewards. It just gets a bunch of data, it has to figure everything out and see what the output should be. So there are no associated target outputs or rewards. The goal of unsupervised learning is to discover inherent patterns, structures, or relationships within the input data itself. For example, data clustering or dimensional reduction. Okay, you can imagine simple techniques like empirical orthogonal functions, which kind of try to find statistical patterns in space and in time, and then they stack up multiple modes which are orthogonal to each other, and then there are many details. So coming back to self-supervised learning again, in self-supervised learning, the data itself provides the supervision without requiring manually labeled data. So that's like unsupervised learning. The key idea is to create auxiliary prediction tasks from the unlabeled input data itself, where the model learns to predict part of the input from other parts. By solving these pretext tasks, the model builds useful representations that capture meaningful information and patterns in the data. Now, there are some details which become clearer if you do applications, but here we are just going through them. So in the report, we will use standard acronyms that bring us back to climate, energy, agriculture, industries, nature, and so on, such as autonomous vehicles, carbon capture and storage, carbon dioxide, electric vehicles, greenhouse gas, global positioning system, generative pre-trained transformers like ChatGPT that you have heard about, graphic processing units which make computations supremely efficient. This is how NVIDIA has become the king of the world now. Heating, ventilation and air conditioning is HVAC, light detection and ranging is LiDAR, LULCC is land use and land cover change, very common in biodiversity and land use change monitoring, satellite data, etc. Metal organic frameworks are used for specific absorption. Let's say they allow molecules to go through, but if you imagine carbon capture with an MOF, it has abilities to absorb CO2 onto its surface, and then you heat it and then desorb the CO2 to capture it, and so on. National Aeronautics and Space Administration, you heard of. Natural Carbon Solutions, NCS, Nature-Based Climate Solutions also are called NCS or NBCS. Unmanned Aerial Vehicles, UAVs. Indians always have trouble with V and W, so we have to touch the lips to say V, and W is different. Anyway, let me leave this here and we'll come back and read some exciting things. This is going to be multiple podcasts. I'm not going to do it in one podcast as I did with some of the previous topics, because this is really important and interesting and relevant and going to be bigger and bigger part of climate and nature, climate change solutions, sustainability, and so on. So we'll come back and see ourselves in the next podcast of this called Key AI Capabilities, and then see where we go with that. Okay, see you.